Okay, class, today we're going to be covering the topic of binary trees. So the objectives, we're going to talk just what is a binary tree. We're going to talk about some of the definitions. We're going to talk about how we use them. We're going to learn about how we can make our own binary tree using a tree node class. And then we'll extend the idea of binary trees to the idea of a binary search tree. So a binary search tree is a specific kind of binary tree. Then we're going to talk about how we use this idea of a binary tree in Java. We'll talk about how Java decides to implement and use binary trees both for sets and maps. So trees are very useful in general for either searching things or for making decisions. We talked about doing a binary search already in class, and so a binary search tree is very useful for doing that sort of thing, very useful for searching. It's also very useful for making decisions. You can imagine, you choose either A or B, and if you choose A, you go down this route, and then based on your decision A, you have more choices, and then depending on that choice, you go down this route. And so decision making, decision type of applications, very good use for trees. Trees are useful for hierarchies, for like folders. You have folders and subfolders of folders, etc. So a variety of useful cases for useful applications for trees. First, some terminology. So when we talk about a tree, we talk about the root node at the top. We talk about a left child and a right child, and this is in the context of a binary tree. So a left child and a right child. We have the leaves at the very bottom of our tree. These are basically nodes that do not have any children. We talk about the number of levels in a binary tree. So in this case, we have 1, 2, 3, 4, 5 levels. There's different ways of signifying what level this is. Some people call this level 0, level 1, level 2, level 3, level 4. Other people start counting from 1. So this is level 1, level 2. So different ways of naming the different levels. And in our class, on a problem, we will try to make sure we specify how we are going to be counting, whether we count from 0 or whether we count from level 1. We have here, again, I've used the term node already, so any one of these elements here are nodes of the tree, and then we have an entire subtree here, which would be a portion of a tree beneath another tree. Binary tree properties. It's amazing how big a binary tree can be with only a few number of levels. So with 20 levels, we can actually have up to approximately 1 million different nodes, 2 to the 20th minus 1 to be precise. So it's a shallow tree can hold an enormous number of nodes, and that's the beauty. We talked about how we can search 1 million elements in 20 steps if it's sorted, and if it's sorted, and we can use kind of a binary search algorithm to find our element. So at every single node we make a decision. Is it greater? Is it less than? If it's greater, we go one way. If it's less, we go another way. When we want to implement our own binary tree, we create a tree node class. And a tree node class is actually very similar to maybe a doubly linked list node that has a previous and a next. In fact, it looks exactly the same, except we call it a tree node instead. And instead of calling one of our references a previous node and our next node, we call it left child and right child. So similar look, it's just we name it a little differently to have variable names that are more representative for a tree. And so once we have this tree node, we can then have some useful methods to get the next, or get the left child, get the right child, get the value at the node, set the value, etc. So this looks this should look very similar to our doubly linked list that we talked about before, but it's just in the context of now a tree. So this should be very familiar, actually, in some sense. It's just the way we think about it. It's not a sequential list from left to right, but it's more like a tree where we have right childs and left childs. Trees just lend themselves to recursion. They're very recursive by nature. And so if we wanted to visit all the nodes of a tree, a very easy way to code that up is via recursion. So if our root is not null, we can start by processing the root value, and then we recursively traverse the left subtree, followed by traversing recursively the right subtree. Here's an example. So if I want to count all the nodes in this tree, for example, I start with my root, and that's one node right there, so hence the 1 here, plus I'm going to recursively count how many nodes are in my left subtree by just calling count nodes again on the left subtree, and then I will also count nodes on the right subtree, just trusting the function to return the number of nodes here. So I add up left subtree plus right subtree plus 1 equals how many nodes I have. And the base case is when we get to the very bottom, when there is no node, when our root is null. At that point we return a 0. Second example, we can copy a tree. We copy a tree recursively as well. If the root is null, we just return null. Otherwise, we make a brand new node whose root is the root's value. So we're creating a brand new node with the root at its value, and then we connect up to the left side a copy of the left subtree, and then we connect to the right side a copy of the right subtree. So we recursively call it here, trusting that we will receive a entire subtree right here, a copy of the left subtree, and we will have a copy of the right subtree right here. So there are 3 ways to traverse through a binary tree. We have what's called preorder, inorder, and postorder. Now we already kind of covered this previously. In a preorder traversal, we process the root first. So when we say preorder, the first thing we visit is the root. So the A node would be the first thing. Then we recursively traverse the left subtree. Then we recursively traverse the right subtree. So in this case, we start with A. Then we traverse in preorder fashion this subtree BDE. And again, we start with the root. So B would be the next element. Then we traverse the D subtree, but there's only D there, so we process the D. Then after we've done the left subtree, we do the right subtree of this BDE subtree, and so then we process the E. So then we finished with this left side of the subtree here, so we go to the right side of this subtree, which just contains the C. In order, same concept, but we just visit the root at a different time. Instead of visiting the root first, we visit the left subtree first, then we visit the root, then we visit the left subtree. So you can imagine here, first thing we do, we visit the left subtree, the BDE subtree. But to do that, we visit its left subtree, which is the D. So we start with D. Then, once we've finished the left subtree, we go to the root. The root of this subtree is B, so that's B. Then we go to the right subtree, which is just E. Then we're done with the left subtree here, so we go to its root, which is A. Then we finish that, and we then process the right subtree, which is just C. Okay, post order. Post order, same idea, but the root is visited at the very end. And you can see here, A is my root, we visit it at the end. We start off with the left subtree, and how do we process the left subtree? We do it in post order fashion. So we start with the left subtree, which is the D, then the right subtree, which is the E, followed by, lastly, the root of this subtree right here, so B. So we finished the left subtree of this, so we go to the right subtree, which is C. Then finally we go to the root of the ABCDE tree. Okay. Now this will just take practice. I highly recommend that you practice this. We have some homework exercises that review this. If you have any questions about this, make sure to reach out. Once you get it, it's not too difficult, but I know the first time you look at it, it might be a little challenging because you have to really think recursively as you're kind of doing this in your head. So just a little bit of review. We have preorder, where we start with the root, followed by the left subtree, followed by the right subtree. We have in order, where the root is done in between the two. And then we have post order, where the root is done at the end. So you could always tell first off if it's in order. If it's in order, you know that the root will be on the leftmost side. If it's post order, you know that the root will be on the leftmost side. If it's in order, you don't actually know. The root can be in the middle somewheres. It could actually be on the left side, or it could be on the right side if there are no, right or left subtrees. So within order, the root can appear anywheres, in this list. Whereas with preorder, you know that the root will always be on the left, or post order, the root will always be on the right. Okay, let's now talk about binary search tree. Now the key word here is the word search. In a binary search tree is a very special kind of binary tree. On the the right side here, this is just a regular old tree. It's not a binary search tree. It's a binary tree, but not a binary search tree. A binary search tree has a very special kind of rule behind it, and the rule is that anything on the left of a node is smaller than the root, and anything on the right subtree must be bigger than the root. And this is true at any level of subtree. So even at this level here, the 8, 1, 12, the left subtree is less than 8, the right subtree is greater than 8. And that's why this is not a BST. At the level where we look at the root being 15, well, this subtree here, 1, 12, 8, all of these are less than 15. But at the 12, 1, 8 subtree level, it's not a BST. 8 is not greater than 12. Therefore, it violates the rule of a BST. Therefore, the entire tree is not a binary search tree. So the binary search tree, if you have a data structure like this, it makes searching for things very, very quick. So, for example, if I wanted to, search for some letter, if I want to search for the letter P, Well, is P greater than M? Yes, it is, so I go over here. Is P greater or less than S? It's less than S, so I go over here. And so within 2 steps, I've found my way. Now, the idea of a binary search tree is it makes searching very quick. And also we're going to talk about inserting and deleting values. And both the insertion and the deletion of values are relatively fast. When I say that, it can be done in roughly log n time, which is pretty good for inserting and deleting values into a sorted tree. You know, just think about an array list. If I had an array list and it's all sorted, if I wanted to stick a new value into it and maintain the sorted nature of the array list, it could take up to, n kind of moves to insert something if I had to insert it kind of near the top of my array list, because then I have to shift everything down in my array list, and that takes a lot of work. Similarly, if I wanted to delete something from my array list, I would remove it from somewhere in the middle, and then I'd have to shift everything up. So inserting or deleting into a sorted array list could be O(n) time. And a linked list would be similarly difficult in terms of inserting and deleting into a sorted linked list. And even worse, searching within a linked list is awful. It's pretty much O(n) because you can only go from one node to the next node to the next node. You can't do any sort of binary searching kind of methods in a linked list structure. So a binary search tree gives you the benefits of log n search, log n insert, log n delete. And here's an example of just a search, a contains method, where we could say, well, if the value that we're searching for is greater than or less than our root, we then either continue our search on the left side or the right side of our binary tree, and we just recursively call it until we find it. And again, this would be a log n type of algorithm. Now we could also just as easily iterate through it instead. We don't have to use recursion to do a search. We just start with our node, say our root node, and then we loop around. If it's less than, then we assign our node to be the left. Otherwise, if it's greater than, we assign our node to be the right. And you can see that we're just iterating here. We're not actually using recursion as a way of searching. And this is just as effective, just as fast. In fact, I would say it's faster. We're not even dealing with recursion here. We don't have to deal with kind of putting things onto a stack to call the function recursively. Okay, let's see. Let's move on from here. Now, some interesting properties of a BST. The smallest node of a binary search tree will always be found by going left, 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 left until you can't go left anymore. And this makes sense, right? Because we know that anything on the right subtree of that node must be bigger than this element here. So this must be the smallest element. And similarly, the largest node is found by going right, 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 right until you can't go anymore. This will be the largest node guaranteed. Now to add a node, we could do that fairly straightforward in a recursive manner where we just say, okay, suppose I want to add the number, let's just say 32. So I say, okay, I want to add 32. So is it bigger than this? Yes, it is. Is 32 bigger or less than? It's less than. Okay, go over here. Is 32 greater or less than? Oh, it's less than. Go to the left. Oh, is 32 greater or less than? If it's greater, then we add 32 down to the right side. So you could see insertion in that case is pretty much a log n activity. It just took us 1, 2, 3, 4 steps to find out where to insert that. So that's the kind of basic idea of inserting into a binary search tree. Removing is a little more challenging. You know, when we want to remove something, we want to maintain the binary search tree nature of it. And so if I wanted to remove this node 50, it's not quite obvious how I remove this 50 and still keep the binary search tree. I mean, if we did it something naive like, okay, I'm going to take the 50 away and I'll just move the 75 up here, that would be a problem. Well, then what do we do with the 60 and the, how do we keep the binary search tree structure? So here's the algorithm for this more complicated case where I have kind of a big tree. I have this node 50 that I want to remove. So the step one is you go to the right subtree and find the smallest node of that right subtree. And we remember to find the smallest node of the right subtree, you go left, 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 left. So here we start with this node here, then we go left until we can't go left anymore. We remove then that number 60. That number 60 here is going to be our new root. So we pull it aside, and then we unlink the 60, and then we connect this right child up to the left child of the 75. We basically promote this subtree to become the left subtree of this node 75, of the, basically of 60's parent node. And once we've done that, we've detached the 60 and we make 60 our new root. So this is a pretty clever way of maintaining a binary search tree, and this is roughly a log n type of activity. At most, we have to traverse down to, the level of the tree, and that's log n steps, and then we just kind of do a few linking and unlinking activities to bring it to the top. So it's actually a very fast algorithm. Now, you can imagine with these algorithms, especially imagine the add. Let's go back a few slides. If I add the number 8, it's going to go down here. Then if I add, if I add the number 6, it goes down here. Then I add a 5, then it goes down here. Then I add a 4, then a 3, then a 2, then a 1. You can imagine at some point, if I keep following the algorithm of doing an insert, my tree can quickly get unbalanced, where it's very lopsided. And so our adding and removing and searching methods will take log n time, as long as the levels of our tree are very nicely managed and we have a pretty, what we call, bushy balanced tree. But if we just randomly add or delete nodes into our BST, after a while we could have a binary tree that's very unbalanced. One with just a lot of nodes along one edge, for example. And so there are some fancier methods that while you're doing the insertion or deletion, you have kind of a way to keep it balanced. So there are some fancy algorithms involved. We're not going to cover it in this class, but just understand that there are some more sophisticated algorithms that are designed to keep the tree balanced so that our adding and removing and searching will be maintained at a log n time. Okay, so we're going to end with just talking about how then Java, what does Java do with binary trees? So Java uses binary trees for sets, and so when we create what's called a tree set, it actually is implemented by doing a very balanced BST. And so we have an adds, and we have a contains, and we have a remove method from a tree set. And when we create an iterator to iterate through that tree set, it will actually do it in order, using an in-order traversal. And when we do in-order traversal, it actually then is basically an ascending order retrieval of values. So we have here our constructor. We can make a tree set, an empty tree set, or we can make a tree set out of a current collection of things that will then create a tree set out of a bunch of items. We also have the idea of tree map. Now, a map is different than a set. A map takes an input value and gives us an output value. So basically, it's like a function table. You give it an input, you get an output. You give it a 5, maybe you get the value 10 out. You give it a 10, maybe you get a value of 17 out. You give it 11, maybe you get some other value of 102 out. So basically, it's an input-output pair. You have your key, which is your input. You have your value V, which is your output. And the way that a tree map is implemented is via a BST, where we can quickly search for our keys in log n time. And once we've found the node that contains the key, we also return the value. So every single node contains both the key as well as the value associated with that key. So here are the constructors for that. And that's it. So that's a binary search tree. They're very useful data structures. So I'm just going to open these up one at a time, and you can just think about them as I do this. And one more page here. This is good to practice, pre-order, post-order traversals. You'll definitely see this on a test or quiz. Okay, class, that's it for today. Have a good day.